Alright, what's going on, everybody? This lesson we're going to look at the mean value theorem, but before we look at the mean value theorem, let's take a look at Rolle's theorem first. Rolle's theorem says that let f be a function that satisfies the following three hypotheses. F is continuous on the closed interval AB, it's differentiable on the open interval AB, and f of A is equal to f of B. Then there is a number C in AB such that f prime of C is equal to 0. All right, so here I've got a little picture of what that looks like. And here's four instances here. You can see here that f of A and f of B are the same. That means their y at A and B, their y values are the same. And you can see that there's a bunch of C values in here, okay, where f prime of C is 0. All right, and remember f prime of 0, that's where the tangent line is horizontal. All right, here's another example. A and B, the y values are the same, and we can see that we have a number C in between AB such that f prime of C is 0. Remember, the tangent line is horizontal. Here's another example. See, the f of A and f of B, they have the same value. And this time we have 2, and then here's a parabola that opens up. You can see that f of A and f of B are the same, and f prime of C is 0. All right. So that's a look at Rolle's theorem. Now let's look at the mean value theorem, and at the end of the video I'll work an example with Rolle's theorem. Alright, so the mean value theorem, it says let f be a function that satisfies the following hypothesis. F is continuous on the closed interval AB and differentiable on the open interval AB. Then there's a number C in AB such that f prime of C is equal to f of B minus f of A over B minus A. Now we recognize that, right? This right here, that's the slope of a line, right? Or equivalently, f of B minus f of A is equal to f prime of C times B minus A. All they did is the B minus A here, they just multiplied it over here. And so you get f prime of C times the B minus A is equal to this. All they're doing is taking this equation and solving it for the numerator. All right. So what does that mean? What does it mean right here, the mean value theorem? Well, what it means is that we have a secant line, right? We got a secant line, and that's 2 points here, and that means that there is a secant line that's parallel to a tangent line at this point C. All right. So basically it's saying that there's at least one point, okay, at least one point, C f of C, okay, where the slope of the tangent line is equal to the slope of the secant line. And I know the way I have this drawn, they may not look like they're parallel, but they're supposed to be. Okay. All right. So another thing we can look at, you can look this secant line here is far away from this tangent line, and we can actually move this closer and see there would be a point here where you could draw another secant line, and that's parallel to the tangent line, and it just keeps getting closer and closer and closer. All right. And then here's an instance where you have 2 tangent lines that are where the slope of those tangent lines are parallel to this secant line here. All right. So that's an illustration of the mean value theorem. Okay. All right. So let's look at an example. It says Verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then, that should be not the find, then find all numbers C that satisfy the conclusion of the mean value theorem. Go ahead and put a then there. All right, so, well, we can do that. Okay, that's not going to be too bad. So, let's see. We got to make sure it satisfies the hypothesis of the mean value theorem. So what do the hypotheses say? It says f is continuous on the closed interval and it's differentiable on the open interval. Well, that's easy enough here. It's a polynomial. It's continuous everywhere. It's differentiable everywhere. Okay. All right. So before we start working it, let's come up here and let's look at the mean value theorem. All right, we're going to use this right here to work the problem. F of b minus f of a is equal to f prime of c times b minus a. All right, so it says f of b minus f of a is equal to f prime of c times b minus a. So for our problem, that would say what? F of 2 minus f of 0 is equal to f prime of c times 2 minus 0. So we need to find all this information here to plug in. So let's see. F of 2 is equal to 2 cubed minus 2, which is 6. F of 0 is equal to 0 cubed minus 0, which is 0. And we have f prime of x is equal to 3x squared minus 1. And so f prime of c is equal to 3c squared minus 1. All right. So we're gonna plug all of this in. So we've got, let's see, we've got 6 minus 0 is equal to 3c squared minus 1 times 2. All right. So that's going to be 6 is equal to 6c squared minus 2. And so we get 8 equals 6c squared. So we get c squared is equal to 8 over 6, which is, what is that, 4/3. All right. And so we get c is equal to negative 2 over square root of 3, or c is equal to positive 2 over the square root of 3. All right. Now, there's our two solutions, for C. But it has to be between 0 and 2. You see that? And so this one's not between 0 and 2, but this one is. And there's your answer. All right. So I hope that made sense. Okay. It's not really that difficult. When you think about it, the only calculus is this part right here where you're finding the derivative. The rest of it is just simple algebra. All right. You've just got to, you go up here and just do what this says. Do what it says, Take this, write it down. All right. All right, so let's look at this one. It says, suppose that f of 0 is equal to negative 3. F prime of x is less than or equal to 5 for all values of x. Okay, so we know the derivative of f is less than or equal to 5 for any value of x from negative infinity to positive infinity. How large can f of 2 possibly be? All right, so we're looking at f of 2. How large can it possibly be? All right, so how can we go about solving this? Well, it says that, well, it tells us that f is differentiable. Okay, it's differentiable. Well, it tells us that f prime of x is less than or equal to 5 for all values of x. All right, so that means it is continuous everywhere. All right, so we can apply the mean value theorem on the interval 0 to 2. All right, so let's see what we get. It's going to be the same thing. We're going to apply this on the interval 0 to 2. All right. So remember, same thing. F of b minus f of a equals f prime of c times b minus a. So we get f of 2 minus f of 0 is equal to f prime of c times 2 minus 0. So let's see what we get. So this is going to be f of 2. We'll leave that. We're going to leave that as f of 2 because, I mean, we don't know what that is. Okay, that's what we're trying to find. How large can it possibly be? All right, and that's going to be plus 3 because f of 0 is negative 3, so the minus and minus is a positive, equals f prime of c times 2. And so that gives us f of 2 is equal to negative 3 plus 2 times f prime of c. All right. So hopefully everything's going good. You're understanding everything. We're just using the mean value theorem. All right. So let's note that we're given f prime of x is less than or equal to 5 for all values of x. All right, we're given that. All right, so that means we know that f prime of c is less than or equal to 5. All right, because see, c is some constant. It's some constant term, and it says that f prime of x is less than or equal to 5 for all values of x. So it doesn't matter what c is, we know it's less than or equal to 5. All right. So if we take the f prime of c less than or equal to 5, let me write this a little better. All right, so if we take this and we multiply both sides by 2, we get 2f prime of c is less than or equal to 10. Well, where in the world did the 2 come from? Why did I multiply both sides by 2? Well, I've got this term here, this 2f prime of c. So I'm trying to get that again down here. So that's, I multiplied both sides by 2. So that's telling me that this term here is less than or equal to 10. See that? So if I take the f of 2, all right, f of 2, which is equal to negative 3 plus 2 times f prime of c. I'm picking back up right here. Okay, I'm picking up here again. All right, so I get that, and I know this is less than or equal to negative 3 plus 10. You see that? I'm not, now remember, now keep in mind here, pay attention. I'm not saying that this equals this, I'm saying it's less than or equal to this, right? Because see, I know the 2f prime of c is less than or equal to 10. So if I add the 10 here, well, this is less than or equal to that, so I know the whole thing is less than or equal to this whole thing, which this is equal to 7. All right? So the largest possible value for f of 2 is 7. See? There's your f of 2 right there. All right. So hopefully that made sense. All right. All right, so let's look at this. We've got a theorem and a corollary. So this theorem says is if f prime of x is equal to 0 for all x in an interval ab, then f is continuous on ab. And then a corollary, if f prime of x is equal to g prime of x for all x in an interval ab, then f minus g is constant on ab. All right. So if f prime of x is equal to g prime of x for all x in some interval ab, then if you subtract the two functions, not the derivatives, but if you subtract the two functions, then f prime of g is constant on ab. That is, f of x equals g of x plus some constant c. All right. So I mean, really all they're saying here is f minus g is equal to some constant, and then they say, okay, f is equal to g plus some constant c, where of course c is a constant. I mean, that's what we've been saying the whole time. All right. So let's prove an identity. Let's prove the identity that inverse tangent plus inverse cotangent is equal to pi over 2. All right. Now, we don't have to have calculus to solve this. Okay? We don't have to have calculus to solve this, but let's use calculus. All right. So let's look at the left-hand side here. Inverse tangent plus inverse cotangent. So I'm going to have f of x is equal to inverse tangent plus inverse cotangent. And then if I take the derivative of f, then f prime of x is equal to 1 over 1 plus x squared minus 1 over 1 plus x squared. All right, that's, you've just got to know those. You've got to know those derivatives. You've already learned how to do those. Go back to the chapter where you learned the derivatives of arctan and all that. Those formulas are there. Okay, and of course we can see this is equal to 0. Okay, for all values of x. So what does this tell us? What does this tell us? So that means, f of x is equal to some number c. Okay? All right, remember c is a constant. How do we know that? Well, if f prime of x equals 0 for all x in an interval ab, then f is a constant on ab. Okay, so f is a constant. All right. So now, to determine the value of c, well, what can we do? Well, c is equal to what? All right, c is equal to what? F of 1, right? Which equals, now, where did the 1 come from? That's just the number I'm using. because it's easy to evaluate the inverse tangent and inverse cotangent of 1. I don't need a calculator for that. You can use any number. Okay, you can use 2, you can use 2.5, you can use square root of 1 million if you want to. I'm just using 1 because it's easier to evaluate. All right, so that's equal to what? The inverse tangent of 1 plus the inverse cotangent of 1, which is equal to what? Pi over 4. The inverse tangent of 1 is pi over 4 plus the inverse tangent of cotangent. The inverse cotangent of 1 is pi over 4, and this is pi over 2. So we have shown that inverse tangent of x plus inverse cotangent of x is equal to pi over 2. Well, I don't guess I need to circle that, but there it is. That's your proof right there. All right. And see, I mean, we use this. We showed that f of x is a constant, and that constant is equal to pi over 2. All right. So here is our last example. This is the one from Rolle's theorem. So it says verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval. And once again, then find all numbers C that satisfy the conclusion of Rolle's theorem. All right, so I've got f of x is equal to x cubed minus 2x squared minus 4x plus 2, and on the interval -2 to 2. All right, so we've got to make sure it satisfies the 3 hypotheses of Rolle's theorem. Remember what they are? Well, that's what? The function is continuous on the closed interval, -2 to 2, which that's the case. It's a polynomial. And it's differentiable on the open interval, -2 to 2. It's a polynomial. So that's easy to verify there. But now we've got to show what? We've got to show that f of a is equal to f of b. All right. So we have f of a, which is -2 cubed minus 2 times -2 squared minus 4 times -2 plus 2. That is equal to, let's see, -8 minus 8 plus 8 plus 2, which that is, it's a -6. Make sure I did that right. Yeah, okay. And then I've got to find f of 2. These two have to be the same. So that's going to be 2 cubed minus 2 times 2 squared minus 4 times 2 plus 2. So that's going to be 8. And yeah, so that's going to be 8 minus 8 minus 8 plus 2. And that is -6 as well. So we've satisfied the 3 hypotheses of Rolle's theorem. All right. So what does it say? Let's go back up here and look real quick. Okay. So it says if all 3 of these are satisfied, then there is a number C in AB such that f prime of C is equal to 0. So let's find those numbers C. So we need to take the derivative. So we've got f prime of x is equal to 3x squared minus 4x minus 4. And so f prime of C is equal to 3c squared minus 4c minus 4. All right. Well, I'll come over here and do it. And so we've got 3c squared minus 4c minus 4 equals 0. All right, and so now we just have a simple quadratic equation to solve. So this thing will factor, I believe. Let's see, 3c, c, And let's see, 2 and 2 plus minus, that work? Minus 6 plus 2, yeah. And so I get C equals negative 2/3 or C equals 2. And so actually on this problem, it's going to be both of them, right? It's got to be in between negative 2 and 2. And of course it can include it there. All right. So, you know, that's the video. It's not a lot, okay? It's not a big section. But, you know, there it is. You know how to do it now. Hopefully it made sense. I hope it did. But, you know, check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all later.